Bear with me while I use these paper notes. It really helps for me to keep it on paper. There's one topic I want to cover before I get into any of this mathematical stuff. Let me start by asking you guys the question. Let's say that I roll a die, and I get the number 5. And I roll it again and I get the number 5. It's a fair dice. We've checked. It's good. It's been unwrapped, new from Vegas. Perfect. Roll it again, I get a 5. I roll it again, I get a 5. And I roll it again and I get a 5. What's the probability that the next time I roll it, I get a 5? I'm telling you, there's nothing wrong with the dice and I'm not doing any tricks. Jack, what's the probability that the next time I roll it, I get a 5? Would you bet on that? You'd bet on it. I knew you would. Joe, would you bet on it? No way in hell, he says. Grace, would you bet on it? Not betting on it. Isaac? He'd bet on it. We got 2 risk takers in the crowd. Heather, what about you? She has no idea. That's a good answer, actually. It's a very good answer. So I don't see Sam here. Sam, are you with us?
Yeah, I'm right here.
You're not showing up on my screen for some reason. Would you bet on it?
No, probably not.
Mm-hmm. Okay. I'm going to give you another example. And then I'm going to name this phenomenon. This is a true life example. My mom, before she was she's incapacitated now with Parkinson's and she doesn't get around much. But before that, when she was only slightly incapacitated with Parkinson's, when I visit her in Florida, what she wanted me to do the most was to take her to these nasty little gambling places that Florida has, which are essentially slots. So you're just playing slots in a smoky room with a nasty stained carpet and the lights are terrible and you're there and you're just playing the machine. You give the money when you walk in and they give you a card. You put the card in the machine and it starts sucking the money out of it. So my mom likes to do that, but she couldn't drive anymore and my father refused to take her because he hated it. So when I would come to visit, although I hate it and I tried very hard to convince her not to do this, she would do it anyway and I would drive her. And my father would give me like $20. He's like, here, press the button every so often so she thinks you're having a good time. So I did it with my mom. So usually I would go in, she would have me sit next to her so she could teach me how to use the machine. This one time, she had me sit, she wanted me to sit next to her, but there was somebody sitting there. So she had a favorite machine, and then there was a person, and then there was me. And I'm pretending to play, trying not to spend my father's money on something stupid. And my mom is having a really good time, but she's not winning. The woman who's between the two of us did not win. So my mom's like, quick, move over. This machine is due to hit any second. She never won at all the whole time she's been here for the last half hour. Sit here, you're going to win within 5 minutes. And I'm like, fine, at least I'm sitting next to my mother, which was the goal, to keep her company. So I go over there and I spend her money for half an hour. And of course I don't win because I never win at gambling anything. So, but she was completely convinced I would win. Then I wanted to get away because there was a lot of cigarette smoke in the corner. And I'm like, Mom, I'm going to go sit at that other machine over there that man who just stood up. And my mom's like, no, don't go there. Didn't you see? He just won a big jackpot. That machine isn't going to hit for days. I said, Mom, do you think these machines are rigged? Now, I did think the machines are rigged. But do you think these machines are rigged? She said, no, it's just how it works, Di. It's the odds. It's the odds. I said, so statistically, that machine, because I was already teaching this class, that machine's not going to hit. Exactly. You know how to do the math. Do the math. I'm like, oh, Mom. So, okay. There's a name for this belief. It's called gambler's fallacy. Fallacy is an error in thinking. Gambler's fallacy, it's the mistaken belief that the probability of an event, a particular event, changes with a long string of the same event. It's the probability, it's the mistaken belief. Mistaken belief that the probability of a specific event, like winning in slots, changes with a long string of the event. Okay, so it's my mother's mistaken belief that the probability of the slot machine coming out a specific way changes with a long string of the slot machine coming out a specific way, a different specific way, but a certain way. It's the mistaken belief that if I roll a dice and I get 5, 6 times in a row, that the 7th time it must come up 5. Or it absolutely won't come up 5 because of the odds. Those beliefs, as easy as it is for our brains to go there, especially, Joe, you're like, I'm not betting on that because it's absolutely done coming up 5, right? That's where your brain was. I could tell by how you shook your head. And that's also a mistaken belief. Either direction, it's a mistaken belief. Why? Because the dice has no memory. It's a cube of plastic. It has no memory. These are independent events. And that's what gambler's fallacy is about. It's about mistaken beliefs about independent events.
I have a question.
Yeah.
So, because like the dice, you know, like that 5th time of you rolling a 1 out of 5,
Yeah.
or a 5 is still going to be, you know, 1 out of 6. You still have 1 out of 6 chances because the dice has not changed.
Yeah. If you are asking the question, what's the probability that this time I'm going to roll a 5? That's different from asking the question, what's the probability of rolling a 5 6 times in a row?
So the odds of rolling 5 times in a row are different than, or they're going to be different than rolling a 1 out of 5 like that one time.
Yeah, because what you're really asking is, when you say 5 times in a row or 6 times in a row, what you're really asking, Isaac, is what's the probability of rolling a 5 and rolling it again and rolling it again and rolling it again? And that is different from saying what's the probability of rolling a 5.
Because
it would be a lot less likely that you're going to do it and do it again and do it again. There's actually some multiplication involved there.
Because they're no longer independent.
That's right. Because they're no longer independent. But if you're just asking it about one time, which is what I was asking, then it's you're asking about an independent event. The same thing happens when we're asking or questions. What's the probability that I'm going to roll a 1 or a 5? That sounds like a lot easier than just asking the probability of rolling a 5. It's easier to roll a 1 or a 5 than it is to roll a 5, right? I get 2 possibilities out of 6. So that's what I'm going to talk about first, is what we call the addition rule. The addition rule comes into play when we use the word or in questions, or imply the word or in questions. So when we say, what's the probability, I'm going to use a small letter P for probability, of A or B occurring, it's equal to adding the probability of A to adding the probability of B. So the probability of rolling a 5 is 1 over 6. Remember that. What's the probability of rolling a 1, or a 5. We get each individual probability and then we add them together. So the probability of rolling a 1 is 1 over 6. And the probability of rolling a 5 is 1 over 6. And we add them together. And this is where some of you really fall down because you forget how to add and multiply fractions, believe it or not, because that was 4th grade, who cares? Well, now it matters. So if you really want to and you're desperate, turn them into decimals and add those. But the other way to add fractions if they have the same denominator is to leave the denominator alone and add the numerators. And if you rather, you can put that into a decimal and say you have a 33% probability that you'll roll a 1 or a 5. Think about it. There's 6 sides to the die. You're picking 2 of them, so you have a 1 out of 3 shot. 2 over 6 is the same as 1 over 3, which is the same as 33%. These events must be independent for this to work. You must be thinking of it as an or question. Next rule, multiplication. This comes into play when you're asking questions that are about and. What's the probability of this and that happening? This happening and that happening. People think about it a lot when they're playing poker. You're not supposed to count cards, but nobody ever said you shouldn't do probabilities. Good poker players are, it's either instinct, they don't realize they're doing it, or they're actively working probabilities. Or they're just having fun and they don't care because it's not real money. But the professional gamblers, they're so good at working these probabilities, half of the time they don't even realize they're doing it. Okay, so sticking with the dice example, does anybody know what snake eyes is when you're rolling dice?
2 1s.
2 1s. A pair of 1s is also known as snake eyes. Okay, so what's the probability of rolling snake eyes is the same as saying, what's the probability of rolling a 1 on 1 dice, and now I have another one, and what's the probability of rolling a 1 on that dice? First thing we can do is, I'm sorry, that plus sign is a bad idea. Take it out, don't use it. That was a mistake, sorry, I do this every year. And it feels like you should be adding, but you should not be adding. I'm sorry, I didn't design probability. It's not my fault. It is unfortunate. So the probability of rolling the first dice, a 1, is what's that probability? Jack, what you got? What's the probability of rolling the first 1?
1 out of 6.
Yeah. And what's the probability of rolling the second one? Grace just finished the problem. What's the probability that the second dice I'm going to roll a 1 out of 6?
I don't know.
Okay, I have a dice, right? How many sides does it have?
6.
Great. What's the probability that I'll roll a 1?
1 out of 6.
Exactly, that's what I was asking.
Okay.
All right, now we get to the hard part. The probability of rolling both dice a 1 out of 6. We've got each individual probability right there. Now we have to know what to do about them. And we are saying the probability of rolling a 1 on 1 dice, and notice that, and the probability of rolling the second one as a 1, we multiply them. Now, here's the part some of you don't remember, how to multiply fractions. I like it when fourth grade comes back to us. When you multiply fractions, you multiply the numerator and you multiply the denominator, and you leave it there like that. You don't have to reduce in this class. I don't really care for reduction or not. You can reduce, but you don't have to reduce. 1 times 1 is 1. 6 times 6 is 36. That's way harder to do than 1 out of 6, right? 1 out of 36 chance means there's a hat. It's got 36 slips of paper. What's the chance I'll pull your name out? 1 out of 36. But there's only 6 pieces of paper. What's the chance I'll pull your name out? 1 out of 6. I would take that one every time, as long as it's for something good, like a sweepstakes. If it's to volunteer for something hard, I want 1 out of 36. So 1 out of 36 is a lot harder to get to, which makes sense. It's harder to roll 2 dice the same. The things that are the hardest to do have the highest point values, not point values, but they beat out other things when you're looking at certain card games. The harder ones to get usually are the ones that beat or trump or have higher points than the ones that are easy to get. 3 of a kind beats a pair. It's harder to get 3 of a kind than it is to get a pair. Because then you're saying the probability of getting 1 and another and another, you're multiplying 3 things together. It's going to become a lot more difficult than just multiplying 2 things together. That denominator is going to grow fast. I'll show you. Let's say I have 3 dice. What's the chance of rolling a 3-eyed snake? 1/6 times 1/6 times 1/6 equals only 1 chance out of, what is 6 times 6 times 6? It's 36 times 6. Jack, you got a calculator up? What's it?
216.
216. Okay, so the probability of rolling 1 is 1 out of 6. The probability of rolling 2 1s together is 1 out of 36. It got much harder. The probability of rolling 3 1s together is 1 out of 216. And there's only 1 in the top, not because it's the number 1, but because it could be any number. This would be the same as I said, the probability of rolling the number 4. The probability of rolling 1 4 is 1/6, 2 4s is 1/36, and 3 4s would be 1 over 216. You can see why certain hands beat other hands in, for example, poker, but other card games as well. Okay, so we have these 2 rules, and I want to go through some examples until you learn these rules. So give me a second to find the, oh my gosh, these are Z-score questions in here. No, never again. No, no more. Okay, let's do some cards. I have a deck of cards. How many cards do I have?
52.
Thank you. 52 cards. We got rid of the jokers. We got rid of the instructions. We got rid of the advertising card. We're down to 52 cards. Okay. What's the probability that I'm going to get the ace of spades? If I shuffle and draw at random, probability of getting the ace of spades, anybody?
One in 52.
Thanks, Sam. Okay. Ace of spades. What's the probability that I'm going to get the queen of diamonds?
The same, 152.
What's the probability of getting the king of hearts?
The same thing.
Thanks. 1 over 52. Okay, what's the probability of getting, if I'm only going to draw one card, of getting, I put these back in and I shuffle, by the way. Okay, what's the probability that I will draw either the ace of spades, the queen of diamonds, or the king of hearts?
Three out of 52?
Yeah, because what you did was you added them together. So you add the numerators and you get 3, and you leave the denominator alone. And if you wanted to, you could call that 0.06. If you'd rather think about probabilities, it's 6%. Okay, that's one set of problems. Right. Some that are more like real life. What's the probability that if a person draws an ace from a deck of cards, any ace from a deck of cards, and keeps it, what's the probability that they will draw a second ace? Don't forget, we still have 52. So the probability of drawing an ace, keeping it, and drawing a second ace. First thing to think about is the probability of each one independently, and then we figure out what to do with them. What's the probability of drawing an ace from a deck of cards?
13 out of 52.
No. What made you say that, though?
Oh, wait, 4 out of
Yes.
52.
Yeah, you're right. I don't know where you. Oh, because you were thinking of a suit.
Yeah.
Yeah. No, it's how many aces. So you were right the second time. 4 over 52. Thanks. So stick with this one for a second, Grace. What's the probability of holding on to that and getting the second ace? What's the, how many aces are left?
3 out of 52.
Yeah, 3, but not out of 52. Don't forget you kept one of the cards.
Oh, 51.
There you go. 3 over 51. And there was an and in the question. The probability of drawing an ace, keeping it, and drawing a second ace. So do I multiply or do I add? Go back and look at these two rules. There, and. So I multiply. See that? Yes, no? I'm waiting for you, Grace, because you're the one that's got your things outlined in green because you spoke last. Might as well finish out the problem. The question is, do we add or do we multiply? With addition, we do that when there's an or there. The probability of drawing an ace or a different thing. But this one wasn't that. This one is the probability of drawing an ace, keeping it, and getting a second ace. So we have each individual probability,